All right, well, welcome to the end of week 2, another lovely differential equations day today. So our plan today is to talk a little bit more about exact differential equations. I don't know that I showed you a whole bunch of examples, but I want to do a few more, including some that have an initial condition, just so you can see how that goes. But really, it's exactly the same as finding the potential function for a conservative vector field. There's another situation where you were doing differential equations, you just didn't know it back in calculus. So we'll do a few more examples of that. And then I'm going to show you a trick to make non-exact differential equations exact, because there are certain forms that they take on that allow us to turn them into exact differential equations. So I'll show you that as well. But before I go off and start doing that, would you guys like to see anything from the homework or talk about anything that we've discussed up to this point? All right, well, I'm hearing nothing and I'm seeing nothing. So I'm going to go with that. We're all good for right now. And yeah, I'm going to hop up to the whiteboard and I'll be right back with you. All right, so last time I introduced you to exact differential equations. So let me remind you what those look like, because that's really what we're going to be talking about today. And the generic form are things that look like this. So again, I'm going to try to use the book notation. So I believe they called that function m. There's some function m of xy, and we're adding to it some other function n of xy times y prime equals 0. All right, so this is the form that we need for a differential equation to possibly be exact. Okay, this isn't enough, but what we need here is where the partial derivative of m with respect to y equals the partial derivative of n with respect to x. So just because you can write it in this form, I mean, just about every first order, no, I think every first order differential equation can be written in this form, but they're not all exact. They're only exact if this relationship holds between the partials of those functions. And then there was an alternate way that we sometimes see this written. So let me go ahead and put that up here too, just to remind you. Sometimes you'll see it actually written as m dx plus n dy equals 0. I'm dropping the x's and y's in those functions, but these are the same functions. But sometimes you'll see it written like this with the dx and the dy. And that's pretty much where we just take this derivative, we split it into the differentials, and then multiply by the dx. So seeing this is also totally fine. If you're in this form, again, with the same my equals nx, then it's an exact differential equation. All right, so that's what they have to look like. And if you get this, if this is the solution, or if this is if the form you have is exact, then the solution it's going to be where we have, I think I called it f of xy equals c, where the partial with respect to x of f was m, and the partial of f with respect to y was n. So again, in the language of vector calculus, this guy was a potential function and you can really think of this as a conservative vector field. So if you go back to fourth quarter calculus, you know, wherever you took calculus at the end of calculus, when you talked about vector calc, that was the language that we used then. So we don't need to call them those now, but it's just good to, you know, relate it back to something that we already. Okay, so the goal is, well, twofold. One, recognizing that it's conservative, recognizing that it is an exact differential equation. And then once it's exact, finding the potential function. So let me remind you about those real quick. How about you can remind me, how can you tell if this is exact? All right, I'm sorry, that's not what I meant, because we already know how to tell if it's exact. How do you find the potential function?
Integrating with respect to y.
Yeah, you do partial integrals. You integrate the m with respect to x and the n with respect to y, right? So this potential function, this is found using partial integrals. All right, so let's just do a couple here to remind ourselves how this works. And we'll do two things. One, we'll make sure that it's actually exact, because if it's not, we can't do this process. And then once we know it's exact, we will find the solution using the partial integral. All right, so how about this one? Let's say we've got y over x plus 6x dx plus the natural log of x minus 2 dy equals 0. All right, so first things first, let's confirm that it is exact, because they're not always going to be exact, right? So let's just see. If we take my, the derivative of this first thing with respect to y, the y over x is going to give us a 1 over x. The 6x is going to give us 0. All right, so then we go to n and we look at nx. The derivative of natural log is 1 over x. The derivative of 2, of course, is 0. So our partials are the same, which means that this is an exact differential equation. All right, well, now let's find our function. So here's what we're going to do. We're going to take that m, and we're going to integrate that with respect to x. So that's going to give us y times the natural log of x plus 3x squared. So I know that my potential function has to have those two pieces, or else the partial with respect to x isn't going to be what we've got here for m. Okay, so then we'll go to n, and we'll do the same thing. So we'll take the natural log of x minus 2, but we're going to integrate that with respect to y. So those are both constants with respect to y. So we get y natural log of x minus 2y. All right, so we did the two partial integrals. And now we're going to put those together by just adding them. So we're just going to take all the pieces that are in here and put them together without repetition. So we're going to get y times the natural log of x plus 3x squared. I don't need to add another y natural log of x, but I do need my minus 2y. So there's my potential function. That's the f of xy. And then, of course, we just set that equal to c. So the reason that this works, and I don't know that I mentioned this last time, but the reason that this works is actually implicit differentiation. Right? Think about if we're going to take this and we're going to differentiate with respect to x. So all the pieces that have x in them, you're going to differentiate like normal, right? With potentially chain rule-y stuff, but you're going to differentiate like normal. The y's, you're going to differentiate like normal, but then attach a y prime. So if you think about this form, the form that I wrote, not the dx dy bit, but the one with the y prime. So think about what we're doing when we differentiate with respect to x. You just get the derivative with respect to x. That's why this is the sub x of f. For the other piece, you're going to get the derivative with respect to y, but by the chain rule and implicit differentiation, that all gets multiplied by y prime. So that's why this works. This is just implicit differentiation. It must work because that's how differentiation works. All right, so not too bad, right? There's our function or our equation, solution to the equation. Now, this is one that I would probably go ahead and solve for y, though, because if you look at it, it's not too terrible in terms of y. There are two pieces with y, so if I keep those and factor out the y, I get y times natural log of x minus 2. If I move the 3x squared to the other side, that's c minus 3x squared. And then I just have to divide by that factor. So this is one we're getting the explicit form is actually quite easy. And so I would go ahead and do it. I would just go through the process and find it. All right. But like I said before, and I think it was Bradley who asked me about this regarding the homeworks. If you get it to the implicit form, I'm happy enough, unless I specifically say, write the solution explicitly. All right, so unless I'm explicit about wanting an explicit solution, you can leave it implicit. All right, so how do we feel about that? Not too bad? Is that a good little review, remind you what we were talking about?
Why again is it equal to just c? Is it because when we integrate, we get, our plus c's, we subtract them over?
It's because it was equal to 0.
Mm-hmm.
Right?
Yeah.
Basically, what we're doing is we're integrating both sides. These are your two partial integrals. And that led to this stuff. And then we have to integrate 0. And the integral of 0 is a constant. Is that cool?
Yep.
Makes sense? All right. Okay, so now this one, obviously, there was no c to find, like we didn't have a initial condition. So let's do one with an initial condition just so you can see that it's like not really a big deal. It's just the one more step. But let's go ahead and do it. So let's say we've got 9x squared plus y minus 1 minus 4y minus x times y prime equals 0. And we'll go with an initial condition of y of 1 equals 0. All right, so again, let's check it, make sure that it actually is exact. So if we do my, that's going to be 1. because the 9x and the -1 both go away. And then what do we get for nx?
1.
Not -1?
Nah, because I want to distribute that minus sign in front first.
Yes, good catch. Man, I thought I was going to get you guys on that one. Yeah, distribute this minus sign through. So it's actually a -4y plus x times y prime. Because remember, our form was m plus n times y prime. Okay, so yes, they are definitely the same. So we are good to go with those. So we'll integrate the 9x squared plus y minus 1 with respect to x, which gives us 3x cubed plus xy minus x. And then integrating -4y plus x with respect to y gives us -2y squared plus xy. So we'll put that all together. So we get 3x cubed plus xy minus x minus 2y squared. The xy is already there. That equals our c. All right, so now let's do our initial condition. Y of 1 equals 0. So if I plug in 1 for x, and I plug in 0 for y, I need to get truth. All right, well, that's 3 minus 1 is 2. So we get c is equal to 2. I'm just going to go ahead and erase that and make it a 2 and call it good. All right, so there is the solution to this initial value problem. And this is also one where I would not solve it for y. I mean, you can. It would require to use a quadratic formula because it's a quadratic in terms of y. Some of your a, b's, and c's are going to have x's in them, and the whole plus or minus, you'd have to figure out which one is, whether you're using the plus or the minus depending on the initial point. More work than it's worth. All right, so you get an initial condition, no big deal, doesn't really change anything. All right, so you kind of like these?
For now.
For now. Well, because I did mention, I don't know if you remember this, but I did mention that most of you guys are going to be pretty comfortable with this because the whole like potential function thing was, well, first of all, it's not new to you. You've seen it. And it's pretty straightforward process. It's not really that complicated. So most students that are in DiffyQs like this. They like it. But the problem is you can have something that sure looks good, right? It's in the right form, everything is beautiful, but it's actually not separable like this one. Let's say I just gave you this. I'm not going to make it too terrible. How about it's just y times dx plus 2x minus y e to the y dy equals 0. So this one's presented to you and you go, all right, cool. It's definitely in the right kind of form for exact. So you go, well, let's just check it. Let's do the old my and nx stuff. And you see that my is 1. And nx is 2. And it's at that point you go, well, crap. It's not exact. So then you start thinking about other forms that you know, and you go, all right, well, maybe can I separate it? you know, you're not going to be able to separate this guy. All right, so it's not separable. Well, it's first order, but it's definitely not linear because of e to the y. And so then you go, nah, I don't know. But then you start thinking like a mathematician. And what's a mathematician going to do? Run
Fake
into
it.
something. Okay, we're gonna fake it, right? We're gonna fake it till we make it. And what do you think we're gonna do? Because I want it to be exact, right? I really want it to be exact because if it's exact, then life is good. Well, that means I need to change this y, and I need to change this 2x minus y e to the y, such that they satisfy my equals nx. Well, since I need to change both of those, the easiest way is if I just multiply by something. If I take this equation and I multiply by something, if I pick the right something, it will make it so that those two things meet the conditions for exact. So I'm going to put in an integrating factor. So this is what we're going to try to do. And we'll do this generically. So suppose that we have m dx plus n dy equals 0. What I'm going to do is I'm going to multiply both sides of this equation by a function that I'm going to call mu. Okay, so this guy mu, this is a function of x and y. And for the time being, it's unknown. But the hope is that I can find said function so that when I multiply it to both of these pieces, I get something that's now separable. All right, now I'm just going to tell you, I'm just going to show you what we could pick for a mu to make this work. All right, and we'll see where this comes from in just a minute. But let's say I just pick mu to equal the function y. Check out what happens if I multiply everything by y. I'm now going to have y squared dx plus 2xy minus y squared e to the y dy equals 0. And if I look at the partials now, my is 2y, and x is also 2y. So by multiplying by y, we turned it into something that is exact, which means it's now something that could be solved. All right, let's go ahead and solve this. If I do that, I'm going to get a y squared x from this piece. And then the next piece is going to give me a minus, going to integrate that with respect to y. Oh, good Lord. Y squared e to the y. That's going to be some sort of integration by parts business. I'm too lazy to do that. But that's going to equal c. And it turns out that this is still going to be a solution because when we differentiate implicitly, there's going to be an extra y everywhere that we could just divide out and reduce it down to this. All right, so this is the goal. is figure out a way that we can figure out what this mu is. Because if I can find it, and I just multiply it through, oh, hell yeah, that's awesome. Because exact are quick and easy. All right, well, it's great when somebody tells you the mu, but having to find it yourself, well, let's see if we can build the process and see what we need to do. All right, well, if we distribute that mu through, look at what happens. This is now mu times m dx plus mu times n dy equals 0. And so let's think about the condition that's needed for this to be exact. For it to be exact, we need my, or we need the derivative of this thing with respect to y. So mu times m, derivative with respect to y, has to equal mu times n, derivative with respect to x. Right? That's what it means for it to be an exact differential equation. So we're taking partial derivatives of products. Now that means we need to use the product rule. So we're going to get mu y times m plus mu times my, and that's going to equal mu x times n plus mu times nx. And I'm going to rewrite this just so that it's a little bit cleaner, a little bit easier to see. And I'm going to write it as the m times mu y. Then I'm going to subtract the n times mu x. I'll bring that over. And then I'm going to have plus mu times my minus nx equals 0. So I just brought these two from the right over to the left. And the ones that have the mu's, I just factored out the mu. All right, so whatever mu is, we have to have this work for us. So this is a differential equation. Do you see it? I hope.
Is it a partial differential equation though?
Yeah, but it's a partial differential equation, and we don't know how to solve those, right? So this right here, this is a PDE, not an ODE. And of course, now that we recognize that, this is when we should all have a big frowny face. Right? Ugh. Crap. All right, well, when you get to PDEs, you can learn how to solve these things. But I'm going to show you a trick that's going to, or certain forms of these that are going to lead to ordinary differential equations. And this is how we're going to pull this one off. All right, so this is just some cases, some special cases. So what if what we've got here, so I'm going to put here, suppose that mu is only a function of x. Let me actually write, suppose mu is a function of only x. Okay, so what if we're in a situation where the mu we need is only a function of x? All right, so mu is going to equal x squared. Mu is going to equal 2x plus e to the x. So whatever, right? Just plain old f. So think about what happens there. Okay, well, in that case, the partial derivative with respect to x of mu is just mu prime. Right? If there is no second variable, then the partial derivative is the same as the regular derivative. And also, mu sub y is going to be 0. If there are no y's, well, that piece is 0. Okay, so come back down here and look at what that does. That turns this thing into, well, m times mu y is m times 0, so gone. We're going to have a minus n mu prime plus mu times my minus nx equals 0. And this thing is separable. If I move stuff around, I'm going to get mu prime over mu is equal to my minus nx over n. My head shadow's getting in the way. Hold on. So then all we have to do to get our mu is to integrate this thing. And we're going to get the natural log of mu is equal to the integral of this horrible fraction with respect to x, which then means mu is going to equal e to all this stuff. So this was a big suppose, right? This was a really big suppose. But if mu is only a function of x, we have a way of finding mu. And if this is going to be a function of x, that means that this fraction, my minus nx over n, this can only be x's. So whatever m and n are, when you take the two partials, the difference in those two partials and divide by n, there can only be x's left. But if that's the case, if there are only x's left, cool. Integrate that thing, take e to that power, and there's your integrating factor. Okay, but I know that's a big if. If that fraction just magically happens to be only x's, then we're good. Oh yeah. If it is only x's, we're good. Now, you can make the exact same argument for what if it's a function of only y? Okay, so here's the other kind of cases. Suppose mu is only y. And in that case, mu sub x is going to equal 0, and mu sub y is going to equal mu prime. So look at what happens to this differential equation. You get m times u or mu prime minus 0 plus mu times my minus nx equals 0. And by like the exact same argument, you can separate it, you can integrate it. And what we're going to get in that case, so I'm just going to put dot, 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 because there are a couple steps to get there. But you're going to get mu is equal to e to the integral of nx minus my over m dy. So it's got a similar structure. The top, the signs are reversed because this was a plus m. This other guy was a minus n. So that's where that ends up coming. But we have the same kind of deal that this is only going to work if this fraction, again, whatever n and m happen to be, when you take the difference of their two partials and divide by m, this needs to be only y, no x's. So if we happen to be in one of those two situations, sweet. That thing turns from a partial derivative to an ordinary derivative. We know what to do. All right, now there are some other forms that work. All right, like for example, if mu is a function of x times y. So there's all kinds of x times y's. X times y quantity squared. Sine of x times y, e to the x times y, right? So if it's all L to x times y's, that works. And there are a bunch of other ones. All right, there are a bunch, and think about it. Differential equations is not that new of a subject, right? Derivatives, I mean, we're talking now over 400 years old. Differential equations have been worked on for hundreds of years. Lots of mathematicians have spent a lot of time thinking about the various forms and have come up with all kinds of them. But these are the two main ones, and they're the two easiest, which is why we start with those. All right. Okay, so this is what we're going to look at. We're going to look at these two fractions, nx minus my over m and my minus nx over n. And we're going to hope that one of them is going to be such that it's a function of only the one variable. And if it is, then that's what we're going to integrate. That's what we're going to use to find our integrating factor. All right, so let me show you how this works. And let's go back to that example, that first one that I showed you, where I said, hey, check it out. The magical integrating factor is y. Now you're going to see where that y comes from. All right, so let's go back to that one. All right, so we had y dx, and then it was plus 2x minus y e to the y dy equals 0. Right. So we already know what mu needs to be because we found it. But let's go through the steps. So think about what we need. We need both of these partials. So always, just go ahead and find my and nx. You should always do that because A, you want to check and see if they're equal to each other to start with. And then if they're not, okay, well then we know what we need to do. So again, my was 1 and nx was 2. And unfortunately, they're not equal to each other. Okay, so here are the two forms of things that we need to look at. So the first one is my minus nx over n. That's the one I got circled over there, right? So we're going to look at this. The other one we're going to look at is nx minus my over m. So that was the other one that we found that's subsequently been erased. But let's see what those things look like. All right, so the first one, my minus nx is -1. N was this thing. So my minus nx over n gives us this. But this is when we get the frowny face, sad face, because this is not only x. Since that's not only x, we can't use this derivation over there. All right, well, let's look at the nx minus my over m. Well, nx minus my is 1. M is y. And this is when we get big old happy face. Because this is only y. So this is one where we're going to be able to pull this trick. We're just going to want to use the second of the two derivations. All right, so here's what mu is going to look like. Mu is going to equal e to the integral of 1 over y dy. So that's e to the natural log of y, which is y. So that's where that came from. So when I first presented this example to you and I went, well, that's not exact. Ooh, but we can multiply by this magical y. This is how we found that y. The fact that this ratio here was a function of only y, we were good to go. All right, so questions on this one before I show you another example?
That's kind of crazy. Because that was a big assumption at the beginning.
Oh yeah, no, it totally is. And so, okay, so what happens if it's not? Like, what if neither of these are a function of only x or y? You got to try something different. And that's really kind of how all of differential equations happened. Was, all right, here's a differential equation, solve it. All right, well, I figured out how to solve this form, but not the next form. Okay, well, try the next form. Oh, I found a way that works for this. Well, that doesn't work for this other form. Okay, well, let's try that form, right? And so every time mathematicians were presented with a new form of differential equation that previous methods didn't work for, they did this sort of thing to find a method that works. And this multiplying by an integrating factor is one of the good old standards. Just go, well, I'm going to multiply by something. I just got to figure out what that something looks like. But yeah, I agree, Bradley, that was, I mean, that is a huge assumption. And it's not going to happen all that often. But when it does, we're gold. All right, well, let's try another one. So how about this guy? Let's say that we've got x plus 2 times the sine of y plus x cosine of y times y prime equals 0. All right, so let's just dive right in. Let's see if it's separable or not separable, exact. It's not going to be exact. But then let's see if we can figure out what we need to multiply to make it exact. Okay, so my is going to be x plus 2 times the cosine of y. And nx is cosine of y. And those are very much not the same. Okay. Well, let's build our two fractions. And let's see what this tells us. So we'll look at my minus nx over n. So x plus 2 times the cosine of y minus the cosine of y over n was x cosine of y. You can divide that cosine of y out of everything, and we get x plus 2 minus 1 over x, which is 1 plus 1 over x. And we actually can stop at this point if we want to, because we know that this is good, right? Because this is only x.
Shouldn't we check though, just in case the other one's easier?
I think we should, yeah. So, and you probably caught it when I said we could stop here, right? We could just go right here, integrate that thing, take e to that power, and there's our integrating factor. But yeah, let's just see what the other side looks like, because it could be something that's easier to integrate, right? And just because one works doesn't mean the other one doesn't work. So let's just go ahead real quick, because we're already here, right? So the other option is nx minus my over m. So that's going to be cosine of y minus x plus 2 cosine of y divided by m. That's the x plus 2 times sine of y. And that's not really, well, no, we're not going to be able to get rid of the y. Right? You could factor out a cosine y on top, divided by the sine of y. You get a tangent of y, and can't get rid of the x's, because you're going to end up with a, what's it like, minus x minus 1 over x plus 2, right? And so this one's no good, because this is not only y. But I do recommend, kind of like what you just said, Bradley, of go ahead and check the other one, because you already have all the pieces. Like, you've already done all the calculus. It's just a matter of kind of punching it together, because there is the possibility that one of them is easier than the other. And if that's the case, pick the easier. All right, well, that was not the case for us here. For our problem, there's only the one that will work, but that's okay. Let's get it. So mu is going to equal e to the integral of 1 plus 1 over x dx, which is e to the x plus natural log of x, which, if we use the rules of logs and exponents, gives us x e to the x. All right, so let's go ahead and solve this. Let's multiply by that x e to the x. We'll see that it is now an exact differential equation, so that we can then go ahead and get the solution to it. So we're going to have now x times x plus 2 e to the x sine y plus x squared e to the x cosine of y prime equals 0. All right. So now we need to integrate those things. All right, so we're gonna have the integral of x squared plus 2x e to the x sine y with respect to x. Well, I'm officially way too lazy. So let's go ahead and crack out a calculator here. So I'm going to integrate x squared plus 2x times e to the x. This is one where if you were going to do it by hand, this would be integration by parts. Probably going to have to do it twice. Oh, that's actually not that bad. That's just x squared e to the x sine of y. So then if we go to the other one, we're going to integrate x squared e to the x cosine of y with respect to y. So the x squared e to the x is constant. Integral of cosine is sine of y. Cool. So we just put those together. They're only the one thing. So we get x squared e to the x sine of y equals c. And I guess if we wanted to, we could go ahead and solve that for y. But yeah, we'll just leave it like that. All right, so there you go. There's an implicit form of the solution to this differential equation. And again, given an initial value, you can plug it in and get your C and everything is great, and blah, blah, blah. All right, so now if I ask you, how do you feel about exact differential equations? You might have a little bit different of an answer, but you really shouldn't. Because think about this. So this entire problem we just did, which portion of this was the solving the exact?
The left part.
Yeah, it was just this. Because by multiplying by the integrating factor, we made it exact, which meant all we had to do is the partial integrals and slap it together. And this is probably the easiest part of the whole thing, right? The heart, where the work is calculating your mu. And that's not anything to do with exact. In fact, that's everything to do with it. This isn't exact, but we wanted it exact. All right, so this method works. And that's really all you should care about. I don't know if you've caught that yet with differential equations. Is now the question isn't, is it easy? Is it hard? No, it's, can you do it? If yes, awesome. If no, figure out another way to make it work. Right? Differential equations is the quintessential don't take no for an answer. Can you apply this method to it? Nope. Okay, find something else. I found another method. Does that work here? Nope. Okay, find something else. And you just keep trying to find something else. Right? And luckily, you guys have had thousands of people before you for hundreds of years figure out all those other options. And I can show them. Okay, but are you ready for this? You're gonna very much not like this. Remember this first differential equation, the one that we just tried here, that we had to go through this process to find an integrating factor to make it so that it's exact? We didn't have to do that. Does anybody see what we could do with that thing? What other method we could try with it?
Separable.
Yeah, that sucker's separable. Check this out. So we'll move that x plus 2 sine y to the other side. So we get x cosine y times y prime equals minus x plus 2 sine of y. We can divide by sine, divide by x. So we get cotangent of y times y prime equals minus 1 minus 2 over x. And that sucker is ready to separate, just to integrate. So on the right-hand side, you're going to get minus x minus 2 natural log of x plus c. And then integrating cotangent, you get the negative. Let's see, I'm trying to remember what cotangent is. I'm going to build it again real quick. So it's cosine over sine. So if we let u equal sine, du is cosine. Oh, I think that's just natural log of sine. In fact, I don't think it is. I know it is. It works. Okay, so now let's get rid of that natural log. So we get sine of y equals e to the minus x minus 2 natural log of x plus c. Let me show you that it gives you the same thing. So you're going to get a c e to the minus x times e to the natural log of x to the minus 2. So that's sine y equals c over e to the x times x squared. And I think you can see it's a really fast. Yeah, we get the same thing. Yeah. All right. So some things to kind of takeaways from this. Right. First of all, it's not going to be always the case where only one method works for a specific differential equation. All right. Often there are lots of ways that work. So I bring that up for a couple of reasons. One, don't forget about ones we've already done, because sometimes, like I think separation is faster. I don't know about you guys, but I think the separation is a little bit quicker if you recognize the separation. So don't forget about things that we've seen before. That's the first thing. The other, second thing, and this is actually really important for students, is I know you guys talk to each other. I know you guys work with each other. I know that you go to tutors and read stuff on the internet and you look at sources. It's very possible that you look at something and go, ooh, I need to try to find an integrating factor and make it exact. And then you go and you're talking to somebody or you look it up and they do it with separation and you're going to think, oh, I did it wrong. But no, you didn't do it wrong. You just did it in a different way. Right? So just be aware of that usually there are multiple methods that can get you to the same place. All right, well, there you go. There's how we can use integrating factors to Yeah. Fake it till we make it. I think maybe you're also starting to see why I like being a mathematician. Like, you guys know me pretty well by now, and you know how I think, you know how I am as a person. And I'm definitely, I've got a little bit of competitiveness in me. I definitely have a little bit of resistance to authority.
Don't tell me I can't do something.
You don't tell me what to do. I tell you, I do not like that, right? And so, like, those things in me definitely lend themselves to being a good mathematician. Where there's the, crap, I'm running into a problem. Let's figure out an end around. And half the time it's, I'll just make something up, and hopefully it works out later. Like, if that's not the story of my life, I wing everything all the time, right? So that's why I was destined to study math. Just everything about it is perfect. Anyway, all right. Yeah, I don't want to move to the next section today. Just so you guys know, we're ahead of schedule. I'm shocked that we're still ahead of schedule, and I want to keep it that way. But we have now just finished chapter 2. So we're going to be heading into chapter 4, and chapter 4 I think is going to help a lot of you, because it's going to be applications. We're going to talk applications of this. You're going to start seeing, why do we care about this, other than just the mathiness of it, right? To a mathematician, why do we care about it? It's that old, why did you climb that mountain? It's like, well, because it's there. Why are you solving these differential equations? Oh, because they're equations to solve, right? So to the math person, yeah, we're doing it because it's math. But for the rest of you, and I know most of you guys are engineers and you're going to be physicists and stuff like that, I want to show you why this stuff matters to you. So we'll start with applications on Monday. And to get to your point, Victor, I don't know, man. I do not know what's going on, because I don't think I've ever, I don't know that I've ever actually been on time after 2 weeks, let alone ahead. So we'll just take it as the math gods are smiling upon us. And Ralph, I'm down with you, man. If we can keep moving and we end up being done a little bit before the schedule suggests, hey, we're done a little bit before the schedule suggests. But we're not going to do that at the cost of understanding, right? Anyway, so with that, let me just remind you, the next set of homeworks are due Monday. I forget which sections they are. I'm not going to speed up the homeworks, even though we're a little bit ahead. I'm not going to speed up the due dates on those, so don't expect that to happen. But you definitely should be able to do everything from chapter 2 now. Right? So with that, have an awesome weekend, and I will see everybody on Monday.